Hi everyone. Today we're going to be firstly looking at condition variables, and like the title says, in the second half we'll be looking into semaphores. Now these are simply just alternative approaches to what we looked at last week, which was locks, which were these structures that allowed us to enforce some sort of synchronization and concurrency, specifically with respect to like shared data. But before we get into that, obviously just a quick recap. Like I mentioned last week, we obviously looked into locks, some specific synchronization challenges, such as the too much milk problem, and then approaches to basically utilizing and implementing locks such as test and set, LLSC, ticket locks, and the last one that we looked into was basically using queues. And while we were looking at all these different approaches to implementing synchronization, we also looked at how we can measure their different performance using some metrics. And in general, we saw that the most widely used approach were variations of what we called spin locks, where threads would just spin or just basically wait until a lock was available for which they could then use and proceed to process some sort of critical section. So just in the same vein as locks, this week we're looking at our condition variables and semaphores, and these are just alternate approaches, like I said, to performing the same type of task. So firstly, in this first half, we're looking at condition variables. Now, here you can see it says that there are many cases where a thread wishes to check where a condition is true before continuing its execution. And an example of this would be, say, a parent might wish to check whether a child has completed its process or its instructions, processing its instructions. And this would be utilized through a function that we used called join. So this is an example of when a thread might wish to wait for a condition to be true. In this case, completion. Now, a condition variable is simply a synchronization object that lets a thread efficiently wait for a change to a shared state that is protected by a lock. So by efficiently wait, that's the key component here. Instead of just like spinning in a while loop until and continually like asking, are you done, are you done, are you done for the child, condition variables do it in a slightly different way, in a more efficient way. So here we have some code basically which would represent that scenario where we have a parent waiting for a child to finish. Now at the bottom here is what we would essentially like to see. The parent begins, the child then is created and starts processing, and then the parent ends. That is the order of events that we would like to encourage. And you can see it's basically represented by this code here. Now, with this scenario, two questions should arise, right? As the child, how do we indicate when we are done? And as the parent, how do we wait for the child to finish? Well, firstly, there is that spin-based approach, right? Where we just idle in a while loop until basically some condition is met. So here what we've done is we've defined a variable called done. Okay, and this variable is used to indicate when the child has completed. So here we can see we create some child C, and then after that we say while done equals to 0 and spin basically, or we'll just stay inside this while loop while done is equal to 0. Now within the child process, we have that it must print it must print the word child, and then update this variable called done. So you can see how we now kind of utilizing a variable which basically is working as a condition indicating when the child is done. All right, the child is not done while it's equal to 0, and the child is done when we set it to 1, and then it is completed. So when done is updated, because this is a shared variable once again, shared across both these threads, well, when done is equal to 0, we're spinning, and then it gets updated to 1, and then we finish, and then that is basically exhibiting the behavior that we wanted to do. The problem with this is that it is, like it says, hugely inefficient, as the parent just spins and wastes the CPU's time. Well, our condition variables basically take this idea of using a variable to indicate some sort of condition, and it implements it in an efficient way so that we don't have to be constantly idling the CPU in like a parent thread. So how do condition variables work? Well, a condition variable has two states, or it can be in one of two states: waiting on a condition. And what this means is that there is an explicit queue that threads can put themselves on when some state of execution is not desired. So when they are waiting, hypothetically, we store them in what is called a waiting list. And it basically just indicates all the threads that are waiting for some sort of condition to be updated. All right. And then the other state that there can exist is one called signaling, or signaling on the condition. Now, some other thread, when it changes said state, can wake one of those waiting threads and allow them to continue. So some other additional thread that isn't waiting, that's basically currently being processed, can change that conditional variables like value, or change the state, and basically wake one of those waiting threads and allow them to continue. So we'll see how this works in a couple examples to follow. But just before we get to that, there are a couple different functions or methods that conditional variables allow us to utilize. And they basically, their function is to shift between these previous two states, between the waiting and the signaling states. So the first function is the wait function, and it takes in a lock structure, or pointer to a lock. Now, what this does is it automatically releases the lock that it receives as an input and suspends the execution of the calling thread. So it's basically performing that wait. And it places it on the condition variable's waiting list until the thread is re-enabled. So it's basically putting, to use some of the terminology from last week, it's basically putting the calling thread to sleep. Okay, it's telling it to pause. It's releasing any lock that thread might have acquired. And it is putting it on the waiting list. Now, this thread is basically going to be here in the waiting list, waiting for some sort of signal to occur or change in state. Now, that leads us on to the second function called the signal. And this takes one thread off the waiting list of the conditional variable and marks it eligible to run. So it's basically the process. We use this method to indicate that another thread can be run. And what it does is it basically takes that thread, all right, one of the threads, and shifts it from the waiting list to the ready list. And then it's up to the scheduler to decide, okay, from there, which process gets processed first. And the last one, and this is not one that we'll really get into, but it is a function, is the broadcast function. And that takes all the threads, so not just one in particular. It takes all the threads off the waiting list and marks them all as eligible to run. So it puts them all on the ready list, basically. So it's kind of like a broadcast signal, and that's hence the name. Okay, so we kind of understand what it is. A conditional variable is a data structure that has a few methods associated with it. Now, how do we actually create one or initialize one? Well, it's just a data structure, so it has a type. In this case, pthread underscore cond underscore t, and we're just giving it a hypothetical name of C. And the specific POSIX calls for wait and signal are represented here. See, wait takes in a pointer to a conditional variable, and as well as that pointer to a lock, which is this mutex object that we looked at last week. And signal takes in a pointer to another to a conditional variable. And just to reiterate, like, what does the wait function do? Well, it takes a mutex as a parameter, so the lock. It releases the lock and puts the calling thread to sleep. And the idea here is that when the thread wakes up again, it must reacquire the lock to be able to continue processing its critical sections. Okay, so here we have our same example of a parent waiting for a child, but now in this case we're using a condition variable. So we still have that done variable that we're going to utilize. We also now have our mutex, which is our lock, and our actual condition variable C. So in terms of child, it's changed up a little bit. Instead of like updating the done variable, instead it calls thread exit. And inside thread exit, or this function that we declared here, we do the updates to the done. Okay. Now this has an additional, quite a few additional components. It has a lock so that it does this in a mutual exclusive zone. So remember, this is a critical region now in between our lock and our unlock statements. And additionally, it also does a conditional signal. So this is what is going to be utilized to wake up another thread. Okay. The other thing to note is we have a thread join function here. And what this is going to be basically representing is the loop in which our parent thread will utilize to wait. How it works, I'll explain it in a little bit again, but just quickly, we acquire a lock, we check if the child is done, and then we basically put ourselves to sleep if they aren't finished. Okay. So now in our main function, it basically reads in similar fashion: parent begins. We declare a thread called P. We create it. This is going to be our child thread. Then the parent calls thread join. So the parent comes into this function here, which is what I was saying, and waits until the child is done. After which the parent will output or display the text parent end. Okay, so what is actually happening? Well, like I said, I'm just going to reiterate basically again, just in case you didn't follow. When the parent obviously is the first process that starts executing, it creates the child thread and continues running itself. Okay, so just in terms of what the parent is doing, it will create the thread and then continue running. It calls into thread join, and in this thread, we're waiting for the child thread to complete. But what is actually happening? So it makes that call to thread join, right? And then it comes into here. So like I said, once again, it acquires a lock. It then checks if the child is done through that done variable. And if it's not done, it will put itself to sleep by calling wait. Now you see here, it calls wait with respect to C, right? As well as M. So what it does with M is it releases the lock M, okay? And with C, it means, okay, I'm going to wait for some sort of change in the state of C. Okay, it's going to wait for a signal on this conditional variable. And basically it sits in there waiting, all right, because it's put itself to sleep here. Okay, then in terms of the child, well, the child will be created. And what is the child process? Well, it's this process, right? So it will print child, and then it'll go into thread exit, and then return after that. So it prints the message child, it then calls thread exit to wake the parent, okay? And inside this thread exit, it grabs a lock, it updates the state variable done to equal to 1, okay? And then it signals the parent, and essentially by signaling the parent, it wakes the parent up. So once again here inside thread exit, we update that done variable equal to 1, indicating that we're going to use this variable to indicate that we are done. And then it does thread conditional variable signal here, the signal function, was C. So it's actually signaling this conditional variable C. And that process basically wakes this thread back up. And by doing that, it will then still be in the while loop though. It has woken it up. Done is now equal to 1, so it can finish this and then exit the thread join function. So that is how conditional variables work in this simple example. Now, you can see there's quite a bit of importance of that state variable done, right? We utilize that to indicate when the child was finished. But this actually creates a few slight issues. Imagine the case where the child runs immediately. Now, in this case, the child will signal, but so the idea here is if the child runs immediately before the parents can actually get to this statement here and put itself to sleep. So that is this case that we're looking at. So the child will signal, but there won't be any threads asleep, right, on the conditional variable. Now, when the parent then runs, it will call wait, and it will be stuck because it will put itself to sleep, and there will be no update to that conditional variable, so it will never wake up because there's no other thread left that can wake it up because the child's already finished. So this is an issue, right? So there is a slight improvement to this approach, but it's still not a solution, okay? And that solution is to say, well, when we're doing thread exit, we do the conditional signal with C, just like we did before. But now instead of using a while loop, we use just an if statement. So here, there is a race condition that emerges, and that's indicated by, well, the parent calls thread join. The parent checks the value of done. It will see that it's 0 and try go to sleep, which is fair enough. But just before it calls wait to go to sleep, the parent is interrupted and the child runs. So just before this occurs, it is interrupted by, say, the scheduler, and then the child will run. So now the child will change the state variable done to 1, and it will signal that a thread should be woken up. But there's currently no threads to be woken, and when the parent runs again, it will sleep forever. So this is another poor implementation because a race condition can emerge. So we've got to think quite clearly and cleverly when we come up with how we implement how we utilize our conditional variables. So in terms of problems, we've looked at those previous two with the while loop as well as the if statement case. Now, another big problem in terms of synchronization is what we call the producer-consumer problem. And this is specifically with respect to bounded buffers. Okay, well, what is a bounded buffer? Well, say we're trying to save data or pipe data from one function to another. We utilize something called a buffer. So here is like a little diagram representation of a bounded buffer. It's basically like an array or a pipe that has a capacity, say, n, and producers will basically feed information in, and consumers will basically take information out. So like I said, producers produce data items, and they place data items in a buffer, and consumers grab data items out of the buffer and consume them in some way. So one example in terms of like the real world case is a multi-threaded web server. So a producer puts HTTP requests into a work queue, and the consumer thread takes requests out of this queue and processes them. Another maybe more closer to home example is the fact that a bounded buffer is used when you pipe the output of one program into another. So if you've ever utilized grep or WC or something like that, you can actually pipe the output of the grep program or the file that grep creates into a process called WC. And this is, again, just like utilizing a bounded buffer. Now, how this works is that this example runs two processes concurrently. grep, as you see here, the grep writes lines from file text with a string foo, with this string foo here. So it basically writes a file with this line in it. And grep is basically working as the producer in this case, okay? And it basically is writing lines from this file to what it thinks is the standard output, okay? But the standard output that we've utilized here is WC. We basically redirected the output of this function using a Unix pipe, okay? And the other end of this pipe is connected to our WC process. And all WC does is basically counts the number of lines in an input stream. So it's given a stream of data and it counts the number of lines. So in this case, WC, or the process WC, is acting as the consumer. And this pipe that is between them is basically an in-kernel bounded buffer. So you remember when we utilized, or I think I briefly spoke about Unix pipe many weeks prior to this, but that's basically what I'm referring to there. So a bounded buffer is a shared resource, and because it's a shared resource, therefore synchronization or synchronized access is required. Okay. So what type of problems can arise without proper synchronization? Well, there are quite a few. For example, producers don't block when the buffer is full. So what if we have a full buffer here and then another producer wants to add data? In most cases, that will just simply overwrite a specific index because the buffer wasn't blocked, or the producer wasn't blocked from writing to that buffer. Alternatively, a consumer consumes an empty slot in the buffer. So what if the consumer tries to access an empty buffer? There's nothing for it to access, correct? So this is obviously an issue. Consumers should be blocked from performing this action. There isn't necessarily there is issues regarding that. Another one is a consumer attempts to consume a slot that is only half filled by the producer. So what if while the producer is writing data to the buffer, the consumer is at the same time trying to read from it? Obviously, this can lead to problems. Alternatively, this is very similar to the first one, where two producers try to write to the same slot. So if you want to rewrite to 0, index 0 here, multiple producers want to do that at the same time. How do you stop this or enforce that it's one at a time without actually just overwriting the variable inside the buffer? And then the other side of the coin, basically two consumers try to read the same slot of information at the same time. So you can see there's quite a few problems that emerge in this producer-consumer situation when synchronization isn't properly implemented. Okay, so let's have a look at this in a simple example. So to begin to understand this problem better, this producer-consumer problem better, let us examine some actual code. The first thing we need is the shared buffer, as you see here, this int buffer. And in this example, it's just going to be a single integer variable, just for simplicity. So it's not like an array or anything. It's just one variable, just a single integer variable. But you can imagine that this could be, this could store a pointer to a data structure instead. So remember also, we want to ensure that we only put data into the buffer when the count is 0. So that's why we have this assert statement. Assert kind of works like an if statement and checks if this is valid If not, it basically returns straight away out of the function and returns like a special signal. But you can just think of it as like an if statement in this case. So if count is equal to 0, meaning that it is empty, then we can put stuff and we update count equal 1. And what do we put in? Well, we put in some value that we receive. Alternatively, the get is obviously when we want to get something. And we use that same if statement assert style feature here. So we check if this count is equal to 1, meaning that it is full. If so, we set the count equals 0, and then we return that value to the user. Okay, so this is our simple put and get, or like get from buffer, put into buffer functions. Now, the only thing that is left to do is write some routines that know when it is okay to access the buffer, to either put data into it or get data out of it. Now, the conditions for this should be obvious by now. I've repeated it quite a few times, but only put data into the buffer when the count is 0, and this is representative of when the buffer is empty. And only get data from the buffer when the count is 1, or in other words, when the buffer is full. Now, if we want to write some synchronization code such that the producer puts data into a full buffer, or consumer gets data from an empty one, we've obviously done something wrong. So this work is going to be done by two types of threads. One of which we'll call the producer, and this is what that thread what that thread looks like here. And the other one is what we'll call the consumer thread, and that's what you can see here. So our producer is essentially, all it's doing is putting an integer into the shared buffer a set number of times based on some condition. Okay, and our consumer gets the data out of that shared buffer until that buffer is empty. So it basically loops infinitely, just waiting for information to be in the buffer. So now imagine that we have just a single producer and a single consumer. Obviously, the put and get routines have critical sections within them, as put updates the buffer and get reads from it. However, putting a lock around the code doesn't work. We need something more. If we just put a lock around the critical sections, you might get cases of deadlocks based upon different scheduling interleavings. So, not surprisingly, that something more is some condition variables. Now, in this broken example, so it is a solution, but it's slightly broken because there's issues with it that I'll demonstrate. We first try to use a single condition variable and an associated lock with an if statement. So here we can see that we've kind of updated our producer process function by including our locks around the two regions, or what we consider the critical regions, as well as an if statement that checks, once again, if a count is equal to 1. And the logic here between the producers and the consumer is that when a producer wants to fill the buffer, it waits for it to be empty, and that's in this P1 to P3 region. It's waiting for it to be empty. And conversely, the consumer has the exact same logic here at C1. I know it's a bit hard to see. At C1 to C3, where it waits for a different condition, a fullness condition, right? Instead of waiting for the buffer to be empty in the producer, we wait for the buffer to be full in the consumer. So this is a simple solution to incorporating our conditional variables into the producer-consumer problem. However, there are two critical problems. So let's understand the first problem, which has to do with the if statement before the wait. So there's this if statement that is causing an issue, as well as this if statement here. So what we're going to do is we're going to have a little look at like a trace of this code, and hopefully you can get a better understanding of where the issue arises. So this diagram here shows the action each thread takes, as well as the scheduling state. So that's these states here. And that can be in ready, running, or sleeping. So obviously sleeping is when a thread puts itself to sleep. Running is when it's being processed, and ready is when it's on the ready list, ready to be processed. So in this example, we need to assume a couple things. So assume there are two consumers, TC1, indicated here, and TC2, and one producer, TP. So one producer, TP. And this is obviously the corresponding state to TP, corresponding state to TC2, and corresponding state to TC1. So in this example, we say first the consumer TC1 runs. So hypothetically say TC1 is running, is the first process to be running. It will acquire a lock at that, if you go back to the code here, C1, acquiring the lock, right? So these variables or whatever indicate like the lines that they correspond with these ones here, just in case you're a little confused with that. So firstly, TC1 acquires a lock, okay? It will check if any buffers are ready for consumption, and that's basically the C2 line. And well, because no producer has run, it will find that there are none, right? So it will wait. So it will come into the C3 here, it will wait and basically put itself to sleep. And this releases the lock. Remember, the wait function releases the lock. Then we'll say, and yeah, the comment here is that there's nothing to get because no producers have been run, so there's nothing in the buffer at all. So then say that, well, then after this, a producer runs, so TP runs, so that's what you can see here. It acquires a lock at P1, okay? It checks if the buffers are full at P2, all right? And by doing this, it finds that the buffers aren't full. And so it finds that it's not the case, and it goes ahead and fills the buffer at P4. All right, so the buffer would be now full at this point. And it updates our count variable, importantly. So the producer then signals that a buffer has been filled at P5, okay? And at P5, if you remember what the code is, we go back to it, P5 here, it's this signal here, okay? And it's signaling on a conditional variable. So this process is going to say, okay, we're going to signal on this conditional variable, and what does signal do? Well, it wakes another thread. Okay, and then after that, it will release the lock. So here, where are we? Here, we're going to basically signal for a thread to be awoken. And in this case, we hypothetically say that TC1 is awoken. Okay, so like I said, the producer then signals that a buffer has been filled. And critically, this moves the first consumer TC1 from sleeping on the conditional variable to the ready queue. Okay, because it's, again, why is it TC1? Well, there is only one sleeping thread, and that is TC1. So it could never have been TC2. Okay, so that's why TC1 is awoken. So it moves the first consumer, or TC1, from sleeping on a conditional variable to the ready queue. And you can see now, instead of it sleeping, it is ready. Okay. TC1 is now able to run, but it is not yet running. So it's able to run, but not yet running. Okay, because it's just on that ready list. The producer then continues until realizing the buffer is full, at which point it sleeps. So you see it continues here, realize continues all the way down here, and realizes that the buffer is now full, and it sleeps. Okay. The producer is then basically moved from the running state to the waiting list. Now, this is the points in which our problem can occur, okay? And it is in this like brief interlude when we have two ready threads and our producer is sleeping. So another consumer, TC2 in this case, sneaks in and consumes the one existing value in the buffer. So over here we see TC2 is scheduled with the scheduler, and it consumes some values with C1, C2, C4. All right, C4 is actually the line that corresponds to getting our data. So if we go back, just in case you don't know what I'm saying, C4 is our get, right? So TC2, or our second consumer, actually grabs some data from the buffer, okay? Now, importantly, you see how it skips C3 here, okay? And it skips that wait at C3 because the buffer is full. So if we see here at C3, okay, if counts is equal to 0, well, that's only updated when the buffer is full, but we've taken something out of the buffer, so the buffer isn't full. So after we have gotten our data, basically our count variable is updated to 0 because we've taken from the buffer. And by taking information out of the buffer, we also trigger the conditional variable for the TP, which basically awakens our producer, which puts it on that ready list. So it hasn't been scheduled yet, but it is ready and wait, so it's no longer sleeping. And then basically TC2 finishes, right? But now what if we assume that TC1, so that original thread that was sleeping, all right, and sorry, it was sleeping, then put onto the ready list. What if we assume that just before returning from the wait, it reacquires a lock and then returns? It then calls C4, which is its get. But at this point, there's no more information in the buffer to consume. So our assertion triggers and the code has not functioned as desired. So clearly we should have somehow prevented TC1 from trying to consume. So we should have prevented TC1 from trying to consume because TC2 snuck in and consumed one value in the buffer that had been produced. So you can see how, because of this like specific interleaving, where we had two consumers both vying for our buffer information, that we could get it to a case where there is no information for our consumer to consume. Now, this problem arises from a simple reason, or for a simple reason, and that is after the producer woke TC1, but before TC1 ever ran, the states of the bounded buffer changed, okay? So after TC1 was awoken over here, but before it actually started running, our conditional variable changed. So, or the states of the bounded buffer changed, which is indicated by this count variable. So signaling a thread only wakes them up. It is thus a hint that the state of the world has changed. Now in this case, that a value has been placed in the buffer, but there are no guarantees that when the woken thread runs, that the state will be as desired. So the idea here is that signals indicate a change in a state, okay? But there's no way of knowing that this change of state is the desired change that a particular thread is expecting. So you see when TC1 was running, the count was 0, okay? So and then it was put to sleep, so it's currently waiting here, or it's sleeping, waiting for that change of condition, and it's expecting or hoping that this, when it's reawoken, that this variable will be 1. All right, that's the ideal case. However, because during that time, TC2 actually ran and stole the data in essence, TC2 updated the states of this count variable to be 0. Okay. And now when it's signaled, when TC1 is signaled and it receives the signal with the count 0 now, it's not actually expecting that value. So signals just tell that a state has changed, but it doesn't tell how that state is changed. So a little bit of a definition or keyword here is that this interpretation of what a signal means is often referred to as mesa semantics. Mesa semantics. Okay, so but this is only the first problem of this code. But first off, let's obviously fix this one, right? So instead of having that if statement here, we're going to change it with a while loop. So a single conditional variable and an associated lock with a while loop. So this solves our first problem, but I'm also going to show you why there is still that second problem. So all that changes basically our if changed to a while here. Same with our consumer, the if changed to a while. So fortunately for that first problem, it's quite an easy fix, right? Just change the if to a while. And hopefully if you think about why this works, you can get a better understanding of maybe how to use these conditional variables. But just think of it now that, well, now the consumer TC1 wakes up and with the lock held, immediately rechecks. So instead of just processing, it immediately rechecks the states of the shared variable, which at C2 here. And obviously the same thing occurs for the producer. Now, if the buffer is empty at that point, the consumer will simply go back to sleep. So it will wake up, check, and then go back to sleep instead of continuing on its execution, which is what happened with our if statement. Now, thanks to mesa semantics, a simple rule to remember with conditional variables is always basically just to use while loops. It's a lot safer than having like an if statement, and there isn't really a downside to it. Sometimes you don't have to recheck the condition, and that would be basically your if statement case, but it's always safer to do so. So just do it and be happy. However, this code, like I said, still has a bug, and it's the second of the two problems mentioned a couple of slides ago. So let's have a look at that second bug, and we'll do that with another trace. So the problem occurs now in the second problem, should I say, occurs when two consumers run first. That is TC1 here, you can see how it runs first, and then TC2 runs again, or second, before any producers have run. And after which, then the producer runs and puts a value in the buffer and wakes one of the consumers. So now we have two consumers on the waiting list. So in this case, a scheduler will pick which one out of the two. And that one will be awoken. So as I was saying, the producer then runs. So yeah, you can see the producer running. It fills the buffer, and that is indicated by the change in the count variable. And then the producer will then awake, or since at P5 we run a signal command, it will wake one of the consumers, in this case TC1. Okay. After which it will continue running inside that loop. And in this process, or in this time, it will acquire and release its lock. So if you just check here, just in case you're not following, it will run inside this loop, right? Until the loop is finished based on this argument. Over and over again, acquiring and releasing its lock. So where does the actual problem occur? Well, it's a little bit later on after this. As you can see, it's coming up over here. So now we have that TC1 is awoken, so it's on the ready. TC2 is still sleeping, and we basically over here, sorry. All right. And we get to a point where the buffer is full. So instead of continuing on, the buffer or the producer now waits on that fullness condition. So it sleeps basically because it's the buffer's full. Okay. Okay, so where are we at the moment? Well, we're at a point where we have one consumer ready to run and two processes or threads sleeping, that being TC2 and TP. Now we're about to cause the problem, right? The consumer TC1 then wakes, and it wakes by returning to C2, okay? And it rechecks the condition, okay? And it finds that the buffer is full based on this count variable. It then consumes a value at C4, okay? So it grabs data. And then this consume then critically signals on the condition C5, okay? But what ends up happening is obviously we're waking up one of the threads now. Now we would want to wake up the producer, but what happens in the case where we wake up the other consumer? So this consumer then critically signals on condition C5, like I said, waking only one thread that is sleeping. However, it wakes up the wrong thread. And because the consumer has emptied the buffer, when we wake up TC2, this causes a problem. This is definitely a possible interleaving or possible occurrence of events. There is no way in terms of our current implementation to enforce that it wakes up a producer. Now that should get you thinking a little bit like we need to enforce that we wake up the producer. So how do we do that? Well, just before I get there, I just want to explain where the actual problem. So over here, we've identified that the problem arises here, but the real reason why there's an issue is that after TC2 wakes up, it will find that the buffer is empty and then go back to sleep at C3. So it will come back to sleep here, right? Because there was nothing to get. So then the other consumer thread, TC1, also goes back to sleep as well over here. And now we have that all three threads are sleeping and there's no thread to wake it up, right? So the issue here is that no consumer should wake up other consumers, nor should producers wake up other producers. The ideal scenario that we want to enforce is that consumers wake up producers and producers wake up consumers. So how do we do that? Well, the simple solution is just to utilize two separate condition variables instead of having both operating on the same one, as well as that while loop, of course. So it's a pretty small one, but it definitely changes it quite a bit. So in order to properly signal which type of thread should wake up when the state of the system changes, in the code, the producer thread waits on the condition empty and signals on the condition full. So here now we have two condition variables, empty and full. It will wait on empty, so it will put itself to sleep on our empty condition. So it's what this means is it's waiting for a signal on empty, meaning that it's waiting for a signal telling us that the buffer is empty. And if the buffer is empty, then it should wake up, right? But it also signals full, so meaning that our buffer is full. And what you would expect then is, well, obviously our consumer should wait on full and signal on empty, and that's exactly what we do. So conversely, our consumer threads waits on full and signal empty. By doing so, the second problem above is avoided by our design, right? A consumer now can never accidentally wake a consumer because they only wake up things that listen or wait on empty, and those are only producers. And obviously the opposite is true as well. Okay. So now that is definitely a solution that doesn't lead to any bugs, but there is one slight improvement that we can make, and that's going to be our solution 4, our final solution. And that is by basically increasing our buffer size. All right, the maximum size of our buffer, or adding more slots to our buffer, should I say. And this allows for more concurrency and more efficiency. We add more buffer slots so that multiple values can be produced before sleeping. Basically meaning that our bounded buffer has multiple values that we can store in it. And similarly, multiple values can be consumed before sleeping. Even with just a single producer and consumer, this approach is much more efficient. Basically, it's more efficient because it reduces the number of context switches, right? If a consumer has to wait for a producer to fill something, and then it fills it like with one item, and then it can consume that one item and then wait again, there's a lot of swapping between producer and consumer. But if you increase the buffer size, obviously you decrease the amounts of context switches, and you can process or transfer data a lot quicker. So yeah, thus increasing efficiency and concurrency. So all we did here is basically added this max parameter, made it basically like an array. And then now our put has changed to incorporate an index like full. And this basically keeps track of where we are within, like how full our buffer is. So if I've used like 3 values, if I put 3 values in, well, the full value here should be 4, etc. Like an iterator variable, basically. And then conversely, you decrease that iterator variable or that like index variable when you want to remove stuff from it. Now, the only thing that really changes here is that our producer only sleeps if all the buffers are completely filled. Okay, so all of those like blocks in the buffer are filled, and a consumer only sleeps if all buffers are currently empty. Okay, so it's not really much of a change, but yeah, so this changed to max. Cool. So that is it for the first half of our lecture, all about condition variables and how they can be utilized for synchronization. In the second half, we'll be looking at semaphores. Thank you all for listening, and I hope it makes sense. It is a little bit more complicated perhaps, but if you work your way through it slowly, think about it a little bit, maybe with debugging the code yourself, it should reveal that it's not too bad.